session today. So we're very happy to have Sabrina from Essen, who's going to tell us something about quadratically refined enumerative.
Okay. Thank you very much for the introduction and invitation. I'm very happy to be here. So I want to talk about, as Michelle said, about quadratically refined enumerative geometry. So I have to tell you what that is. I assume maybe only a few of you have seen this. Probably most of you haven't. So what do I mean by this? So maybe I should start telling you where I come from. I got my PhD in Oslo, where I learned about A1 homotopy theory. Maybe you know about this, rather know the name motivic homotopy theory. And this has many applications to algebraic geometry and also to enumerative geometry. It allows you to do enumerative geometry over an arbitrary base field, and it gives you a refined answer to questions in enumerative geometry. And the answer is a quadratic form, and that's why it's called quadratically refined. So I was planning to just give an introduction to this. So what I do is I will start with some classical algebraic topology. So this is more like a first course in algebraic topology in the beginning. So let's recall the main ingredient we'll see later in a new setting. But now let's do this classically. Let's assume that we have a map of n spheres. Then this induces a map in nth homology, like this. We all know that the nth singular homology with z coefficients here is isomorphic to the integers. Here I choose the same isomorphism, so I get a map from the integers to the integers. And, well, if we all know from algebra that this map is determined by where the 1 goes, and this I want to call the degree of f. So we get the degree map, which sends an endomorphism of n spheres to the integers. And now when I write these brackets here, what I actually mean is homotopy classes of maps. This is maybe too small. Homotopy classes I wrote here. Because of course, two homotopic maps will induce the same map in homology. So this, I can quotient out homotopy classes, and this turns out to be an isomorphism. So here's a way to compute this. Let's assume we have a point in, now I want this to be in the target, and let's assume that the preimage of this point is finite, so I have finitely many points, which I want to call Q1 through Qm, and I take a Q here in here. Then I choose a small ball around Q, and also a small ball, I call it V, around P. And then I can do the following. I restrict my F to U. And let's assume that I've chosen U small enough that it will completely be mapped to V. And then I collapse the boundary, but this is homotopy equivalent to collapsing everything but the point Q here, and here everything but the point P. You could also just collapse the boundary. Let me call this F bar. It's the image of this. But this, writing it like this fits better with what I will write later. So this is homotopy equivalent to the n sphere. This too. So I can take the degree of this, and I want to call this local degree. and I write degree QF for the local degree at Q, and this is just supposed to be the degree of this F bar. And then the degree of the whole map can be computed as a sum of local degrees. Like this. Right. One can actually do this in a more general setup. Maybe I'll come back to this later. So what do we need here? I need this isomorphism to the integers. This is we can do because Sn is orientable. So the top homology will be isomorphic to the integers, and this is an orientation of Sn. So I can replace both my Sns here with oriented manifolds. And then I can do the same story. I can write down this as a sum of local degrees. So I can replace the Sns by, let's say, oriented, closed, so I mean compact without boundary, and manifolds. Let's say x and y, and define the degree of f from x to y. And then I can write it as a sum of local degrees. So what does this have to do with enumerative geometry? Here's one thing. One more thing I want to recall from the classical story, namely the Poincare-Hopf theorem, which I'll state in the following way. Let's say we have an oriented, closed, and manifold. And let's take a vector bundle over it. I also want this to be oriented of rank n, because then, oops. If I take a general section, let's call it sigma, this will have finitely many zeros because the rank matches up the dimension. So this is a general section. And in this case, I can do the following. I can compute the degree of the Euler class of the vector bundle as the sum of local degrees. And now I take 3 images of zeros of my section. So I haven't really told you what this is, so let me just do this orally, because I don't have that much time. So it really is the same construction as I did here. So I have an oriented closed N manifold. So around each pre-image of 0, I can choose oriented coordinates and take a small ball around it, and with these oriented coordinates, when I collapse this, I get a homotopy equivalent to Sn. Then if I choose this small ball small enough, I can trivialize my bundle here around the point. So I get to map to Rn, and I can also just collapse Rn minus 0, and then I can take the degree of this. So this one we want to remember. And then now there's still no enumerative geometry, but as you probably all know, is many problems in enumerative geometry can be solved via linearization. So here's a very famous example for this. Namely, let's take the lines on a smooth cubic surface. Then let's take a smooth cubic surface. That means I take the vanishing of a degree 3 polynomial in P3. So this is of degree 3. And then I claim that this polynomial or this cubic surface defines a section of a certain vector bundle, namely the following. So this defines a section, let's say sigma f, of the following vector bundle. So V here is sim3 of the dual tautological bundle to the Grassmannian of lines in P3, and this is my X in this case. So this here is the Grassmannian of lines in P3, or alternatively 2 spaces in 4 space. And here this is the third symmetric power of the dual tautological bundle. In other words, let me just tell you what the fiber is. So if I take a point in here, so this is a line, so let me put brackets around this to say that I take the class of a line. So then the fiber here consists of all degree 3 polynomials on the line. And how does my cubic surface give me a section of this bundle? So this should go into the other direction. Right, so sigma f should go into the other direction, and it should send a point in the Grassmannian, which corresponds to a line, to just f restricted to L. So why am I doing this? So now this Poincare-Hopf theorem says something about the zeros of a general section. And I claim that if I take a smooth cubic surface, then this is general. So now, what are the zeros here? The zeros are the lines where f restricted to the line is 0. So the zeros are exactly the lines that lie on my cubic surface. And I called it Z. Yeah. So I have some more space here. So now I can, with this restriction, I can translate the problem of counting lines on a cubic surface to counting zeros of this section. If we go to algebraic geometry and do this over the complex numbers, so over C, what happens is that we've seen that the number of zeros equals the number of lines. And since this is a general section, and here the rank is the same as the dimension, and this is the degree of the top Chern class. And you probably all know that this is 27. Now I want to do this over the real numbers. And here I want to use my Poincare-Hopf theorem to tell you or as an intuition of what happens here. So we see that for each line on the cubic surface, we get summoned the local degree. Now there's a result that says that if I take a smooth cubic surface, all the lines are simple. That means that actually the zeros here are simple. In particular, the Jacobian doesn't vanish, and locally around the zero of the section, we have a homeomorphism. So locally around each zero, we have a homeomorphism. So if I do this construction here, I get the homeomorphism. So my induced map on homology is an isomorphism. So the degree is either 1 or -1. That's the only thing that can happen. Otherwise, it has to have an inverse. And isomorphisms of the integers are, that has to be 1 or -1. So over R, each contribution of each line contributes either a plus or -1. So here the Poincare-Hopf, I just write PH theorem implies that this degree of the Euler class of V gives us a signed count of lines. So I either assign a plus or -1, and this is always 3 because the left-hand side does not depend on the chosen section. However, of course, the number of real lines, that this can differ. There could be 27 real lines, but there could also be just 3 real lines. So this is not invariant anymore, but if I do the sign count, this is invariant. Okay. So let's see. So now what I want to do is I want to do this over an arbitrary field. And the intuition really is this Poincare-Hopf theorem. As I said, I come from A1 homotopy theory. Roughly speaking, this is we want to do homotopy theory over on the category of smooth varieties over a field K, or even a more general base scheme, but let's stick to K, a field K. And this works, and we get all kinds of construction from algebraic topology. In particular, we have a degree. And what Kirsten Wickelgren and Jesse Kuss did, they just said, well, we have a degree, so let's just replace this local degree here by this new degree. And then we get something meaningful over an arbitrary field. And here comes the quadratic in. This degree map, I will present to you in a second, is actually valued in quadratic forms. So let's write all of this down over an arbitrary field. And when I mean arbitrary field, I want to exclude characteristic 2 because there funny things happen and it still works, but you have to be careful. So for simplicity, just assume characteristic is not equal to 2. So here's the history. Morel and Wojewodsky, they said, well, we want to have all of these nice techniques like homotopies and the degree for algebraic varieties over K. So let's do this. And they developed what is now known as motivic homotopy theory, or Morel prefers to call it A1 homotopy theory. Here, the A1 is really, well, what is the crucial input for a homotopy? A homotopy, you need the unit interval, and here A1, you can naively replace the unit interval with the A1. We also have a 0 and a 1 here, and you can write down a naive homotopy. But it's much more complicated than that. So what should this be? So this is homotopy theory on the category of smooth algebraic varieties. Over the field K. And let me just tell you this works. It's a quite technical construction. I don't have time to introduce this, but I'm happy to talk about this afterwards. But as I already said, in particular, we have a degree. And this was found by Morel, and we call it A1 degree. So here's how this looks like. Let me decorate it with an A1. So, yeah, perfect. Here's the old degree. So we want homotopy classes of endomorphisms of n spheres, so we need a replacement for the n sphere. And here's a suggestion for that. I take affine n space and I collapse affine n space minus the origin. Well, intuitively, this makes sense. We did something similar here, and we said it's homotopy equivalent to an n sphere. Now you might complain that this is not an algebraic variety, but the first step in constructing this homotopy category is resolving these issues and adding all kinds of small limits and co-limits. In particular, we have quotients like this in our category. It's not an algebraic variety anymore, but it's an object in our category. So here we have our map of n spheres. So we want to take them, again, up to homotopy. Let me also write an A1 here to say that this is up to A1 homotopy. And now this is valued in the Grothendieck-Witt ring. Okay, so don't be confused. This is not Gromov-Witten. This is Grothendieck-Witt. This is something new. And this is where the quadratic comes in. So here I'm being kind of vague. I'm not telling you what that is, but I should really tell you what that is because this is where we want to compute later. So what is this? So this is the Grothendieck bit ring of our field K. It just works. Someone identified it with this Grothendieck bit ring. There's some special maps in here, and they have some meaning as quadratic forms. I don't really have an intuition other than that. It kind of falls out of this. Like, there's different descriptions of this. Yeah. Just, I mean, you can also just define this just algebraically. I would also do this in terms of generators and relations, and this is pretty much what you get. Okay. But, yeah. Okay. So what is this? This is the group completion of the following. So as a set, I take, as I already said, the isometry classes of quadratic or non-degenerate quadratic forms over K. So this is this as a set, but I want a group complete. So I need a monoid structure. And there I take the direct sum. So I can take two quadratic forms and I take the direct sum. I get another quadratic form. So I get a monoid structure on this set here. So then I get a group, but I say it's a ring because I also have a product, namely the tensor product. Okay, but as I already said, I want to do computations in there, and this is not the very good descriptions to do computations because, yeah, I don't know, it's not so good. But here's another description of this. So remember that when the characteristic is not equal to 2, then any quadratic form can be diagonalized. So I can write it as a1 x1 squared plus a2 x2 squared plus ... plus an xn squared. But this is just the direct sum of n quadratic forms on a one-dimensional vector space. The first one is a quadratic form, this is a quadratic form, and I take the direct sum of these and I get this. So these are my generators. So I get generators, and these are denoted by bracket A, and this is really the class of the quadratic form ax squared. And what is A here? Sorry. A is an element of K, but should be non-degenerate, so I take the unit. So this is K minus 0. Subject to the following relations. The first relation is pretty easy to see. Bracket A should be bracket AB squared. Why is this? Well, this class AX squared is the same as the class of AB squared X squared because I can just do a change of variables and replace X by BX, and I get that this is the same class of quadratic form. Then I also need to tell you what happens if I add two generators and multiply them. So let's start with adding. Then what we get is A plus B is AB, A plus B. And if I multiply them, I get just the product. Maybe let's look at some examples. So what should the Grothendieck ring of the complex numbers be? So the first relation tells us if I have an element in the complex numbers which is not 0, the first relation tells us that, well, A is the same as the square root of A squared. And C is algebraically closed, so I always have a square root. So what squares? We only have one generator. Also, these relations become trivial here, because I could just replace any A and B here by 1, by the same argument. So I get the free abelian group in one generator, and this is just the integers. Let me do another example, namely the real numbers. And here, well, I can't take a square root of -1, so I can't try to do the same thing. So this will be a little bigger. This is the polynomial ring over Z, where I join as the cyclic group of order 2. And now, as I already announced, Jesse Kuss and Kirsten Wickelgren just thought, like, okay, what if we just replace the degree here by the A1 degree? This was in 2017. Right, and they want to replace this local degree by the A1 version of this. This is the Q A1 sigma in this Poincare-Help theorem. And then let's just make it the definition. So definition, and let's call it A1 Euler number, because it's the degree of an Euler class. But it's an A1 version of this. So I want to denote it by n A1, again of some vector bundle. And we want to define this to be the sum of local A1 degrees, like this, where we again sum up over all the zeros of a section. So I need to tell you a little bit about the input here. So here, this here is the vector bundle, B for vector bundle, again of rank n, let's say, over a smooth proper K variety. And this is, of course, also of dimension n, like this. And now I haven't told you everything. Here we also have some orientation conditions. We still need these, but we can actually do this in a more general setting. Even in the real picture, you could do it in a more general setting, but it's the same as here. Didn't plan this so well here. So we want this, the following orientation condition. We want that this vector bundle is relatively oriented. So what do I mean by this? So here I wanted both the manifold and the vector bundle to be oriented, because I wanted to choose oriented coordinates and then oriented, or a trivialization compatible with my orientation. But it could happen that both are not oriented, but the non-orientability just kind of cancels out in the following sense. I want the following line bundle to, we have an isomorphism, let's call it rho, of the following line bundles. I start with the determinant of the tangent bundle, and I go to the determinant of the vector bundle, and I want this to be isomorphic to the square of a line bundle. So here, maybe this one here is a line bundle on X, some line bundle. So why is that a good condition? In the end, it works similar to before, as before. So we have a section here, a general section again, and we want to choose local coordinates. This choosing local coordinates gives us a local section here of the first part. Then we want to choose a trivialization. This gives us a section here of the determinant of the vector bundle. And if I choose these so that if I map this to the line bundle here, this section is a square, then I say that this is compatible with the relative orientation. Why does this make sense? Well, if I choose different coordinates here and a different trivialization, still compatible, what I get is something that differs by a square from my first choice. But in my Grothendieck grid ring, when I do my calculation of the local degree, then also this will differ by a square. And the first relation up there will tell you that this is actually the same element. So maybe this was too fast. Maybe I should stop for questions here. Okay. Then you can still think about questions while I'll erase. Yeah? Yeah, classically you would not do it in this way. So get some definition. So also maybe that was also bad notation because V here is my vector bundle, and earlier V was an open ball. Maybe that's the confusion. The open ball one. Yeah. So V is an open ball, and then there's a point in here. I think for V it was P. So I take this out. And then I define a homotopy that sends everything here to the boundary. And then what I do when I quotient this out, this is homotopic to just quotienting out the boundary, and this gives you an n-sphere.
Oh, okay. So you're not literally taking the quotient topology where you do everything that's not together.
Well, it's homotopic equivalent to that. But yeah. No, maybe this is actually, maybe I should have written it like this because I actually didn't use it. But did I erase my local degree? Right. Maybe I wanted to say like, in the algebraic variety case, I can't just homotop everything to the boundary. So there I actually have to do it like this. I have to take in a Zariski open subset, and then I collapse this minus a point, and I say that this is my sphere. What? This collapsing, well, you really just define this as the co-limit of the following. So the thing is, here this is a point. So I collapse this to a point, and I define this as the co-limit of this diagram. And this A1 homotopy category, the first step in defining is embedding it into the category of pre-sheaves, and there you can do these kind of constructions. So this is not a variety anymore, but you have these co-limits in there. So you have pre-sheaves, so have functors to sets, and you just do this on sets pretty much. Yeah. Which category? Oh yeah, you take the category. You can start by doing this. You take the category of pre-sheaves on smooth schemes or smooth varieties over K. So this is the functor category of contravariant functors. Let's start with sets like this. So this is functors here, and then you can define this. You do this object-wise. Yeah. Yeah, I wanted to avoid these technicalities, but yeah, thank you. Thanks for asking. You can just take this as a black box. You just, well, yeah, it works. Yeah, that's what I usually do. Yes?
Those determinants in get Tx and get V, are they spaces?
No, these are determinant bundles. This is the tangent bundle, and you take the determinant bundle of it.
Is it number or space?
No, it's a line bundle. It's like for each. This is a vector bundle, and you take the top wedge of any. It's like the top wedge of this this vector bundle. So for each fiber, you take the top wedge of the vector space.
I have a basic question.
Yes.
If I this A1 degree,
Yeah.
if I thought about this as like kind of second order information, would that be completely wrong? Like you know, I have a function and tangent spaces give me first order approximation, and this gives me second order. Is that completely? That's just nonsense, right? Okay, well, I guess it's nonsense.
Maybe.
This seems like trying to understand it.
Great. Okay. Let's actually apply this now. So where was I? I defined this A1 Euler number, and we've seen that over the real numbers, the Poincare-Hopf theorem kind of gives us an interpretation of the Euler class, or the degree of the Euler class, as a signed count of lines on a smooth cubic surface. And now we replace the degree in the Poincare-Hopf theorem by the A1 degree, so we get something more refined. So here's this example. By Jesse Kuss and Kirsten Wickelgren. So a quadratically refined, I finally used the title, count of lines on a smooth cubic surface. What is this? This is this A1 Euler number I've just defined of our bundle, so Sim3 dual tautological to the Grassmannian of lines in P3. And they computed this to be 15 times 1 plus 12 times minus 1. So here, the 1 and the minus 1 are these generators up there. So, right. So, and I said here, over the complex numbers, we had the 27. So let's check if we get this back. We've seen that the Grothendieck-Witt ring of the complex numbers is the integers, because the 1 is the same as the minus 1 by the first relation. So this is just the same element. So I get 27 times bracket 1. And this is, I want to say this is the rank. This is the dimension of the vector space that the quadratic form lives on. Gives it back the complex count. And if I take the signature, saying I sum this up with a sign, 15 times 1 plus 12 times minus 1, I get the 3 back. And this is actually the same as the sign count over the real numbers. So if you had 27 lines on a smooth cubic surface, then this ones and minus ones would exactly agree with the signs here. But this may make sense over any field, and it's invariant over any field. So no matter what cubic surface I take, we get 15 times 1 plus 12 times minus 1. But I haven't told you why it's invariant. I should really add this, so let me put this here. Because here, this was a theorem. Like the left-hand side didn't depend on the choice of section, but now we took this as a definition. But a theorem of Tom Bachmann and Kirsten Wickelgren says that this is actually independent of the choice of section, or this A1 Euler number is independent of choice of section sigma. Okay. So I want to give you some more examples. I thought of things you might be interested in. So the first example I want to give you is the count of lines on the quintic threefold. When I started my PhD, that was in 2017, that was in August 2017, that was exactly when this paper came out. And Kirsten Wickelgren was one of my advisors, and she gave me the following task. She said, well, do this for a quintic threefold. This was a little bit harder. The first computation of this just used that this is independent of the section, choice of section, so you could just choose your favorite cubic surface and then compute this by hand. But on a quintic threefold, over the complex numbers, there are 2,875 lines, and then doing this by hand gets more complicated. So you had to be a little bit, I had to be a little bit clever. But I finally got there. So this is me. So I computed the quadratic refinement of the count of lines on quintic threefold. Here's what I get. So again, this is the A1 Euler number of a bundle that looks very similar. So I get the quintic threefold, so a degree 5 hypersurface in P4. So by the same argument as before, I just have to take the fifth symmetric power of the dual tautological bundle over now the Grassmannian of lines in P4. And what I got is the following. I got 1,445 times 1 plus 1,430 times minus 1. And again, if you take the rank of this, which would give you back the complex count, you just sum up this 1,445 and the 1,430, and you get your 2,875 back. If you take the signature, so you do the sign count, you get 15, which is indeed the real count, the real sign count. This was done not too long ago by both, first there's a paper of Okonik Telemann and Finashin Kalimov. Okay, so I actually did this quite similar to here. I took the Fermat quintic threefold, there are infinitely many lines there, but only 2,875 deform when you take a general deformation, and I computed these local A1 degrees of these deformed lines. But it turns out the guy who's now my boss did this faster than me. So Mark Levine was a little faster, and he did lines on hypersurfaces of degree 2 and minus 3 in Pn in a different way, not this with this local computations. So you can also do this. I'm not giving you the numbers, they get really big. So this has been done. Then afterwards, we wrote a paper together where we computed not just the number of lines on quintic threefolds, but higher degree curves, namely of twisted cubics, so degree 3 rational curves. And here's what we got for this. We got 317, 206, 376, 375, sorry, has to be odd, minus 765 divided by 2 times 1 plus minus 1, and now I add 765 times 1. So also here, if you take 1 to be minus 1, then the 765 cancels, and we're left here with this big number, which is the classical count by Ellingström-Strömmer. And if you take the signature, then the whole first summand vanishes, and we're just left with the 765, and this has also been computed before by Johannes Weicher. Okay. Okay, so, but there's much more. But I want to finish my talk and talk about my current research in the last 15 minutes. So hopefully I'll get to say something there. So one other big problem in enumerative geometry, you probably all know, is the count of, let's say, rational plane curves through 3D minus 1 points, where D is the degree. Let's keep it simple. So let's only look at rational plane curves of degree D through 3D minus 1 points in general position. So I'll do this in the same way I did before. I start with the complex numbers. What can we say here? Let's ND be the number of these curves. And over the complex numbers, just as the lines on the cubic surface, this one here is invariant. So this doesn't depend on the configuration of points. Oh, choice of 3D minus 1 points. Okay. There are recursive formulas for this. Well, you can think about what happens in degree 1 and 2. There it's pretty simple. You just get 1, because the line is determined by 2 points. The conic is determined by 5 points. And then there are higher numbers, but yeah. What about the real numbers? There, again, it does depend on the choice of points. But again, if you do it with a sign, it does not. You get an invariance again. And this invariance was found by Rochinger. And what he observed is the following. So these plane rational curves from degree bigger or equal to 3, they will have nodes. And he observed that there are 2 types of nodes. Namely, we have the split node. So locally, this is defined by the following equation. So x squared minus y squared. So of course, as in the real picture, this splits up as 2 branches. And then we have the solitary nodes. And this is locally defined by the equation x squared plus y squared. And here we have 1 real point and 0, 0 here, and 2 complex conjugate branches. Now let I be the number of solitary nodes. And then this determines the sign, this number. I still have some space here. So, theorem of Bertinger. Let's call it W, the sign count of plane rational curves of degree D through, so this is all real, 3 minus 0.1, also real points, we count this with a minus 1 to the I, where I is this number of solitary nodes, is invariant. So again, we have a sign count here and a non-sign count here, and the Grothendieck ring of the real numbers, only the ones and minus ones mattered. Here, only the ones mattered. So this really has to be, there has to be a way to generalize this. I'll tell you how. So now it really, it will also depend on the types of nodes, but we will have more nodes. So for other fields K, we can have the following types of nodes. Let's say K rational nodes, because of course they could be defined over a field extension. Again, we have the split node, but now I write the local equation for this a little bit different, but it's the same in the case of real numbers. For D as a square. So this is, again, a split node, because this will, again, have two branches over the real numbers. If this is a square, so I want D to be a square, so it's positive, so I can replace y by the square root of D times y, and then I get the same as the equation here. And I, again, have solitary nodes, given by the same equation, but now D is not a square. And here, I actually want to identify all of these nodes. But here, there are different types of solitary nodes. Because I want to define my type of a node to be this D, but just put in brackets. Let's call it node Z. And I write type of Z. And I want this to be this D in bracket. And where does this live? This lives in the Grothendieck grid ring of the residue field of Z. Okay. And now, with what contribution should I count a rational curve? Let me call this Q well for quadratic version J of C. So C is a rational curve. This I want to be the product of these types. And here Z is a node. But as you see, they might live in some field extension, and this should be in the Grothendieck grid ring of K. But then what I just do, I take the norm, really the field norm of this, and I will land in K. So this lives in the Grothendieck ring of K. But taking this norm is really just taking the correct representatives of this D. And then this is just the product. You can check that this actually, let's check that this actually agrees with this -1 to the I here. So here all the split nodes would contribute a 1, while here this would be positive, so it would also contribute a 1 in brackets. And all the solitary nodes would contribute a -1. So the type would be -1 in brackets, and this actually agrees. And then Mark Levine showed that counting curves with this is an invariant. So maybe let me call this now Q and D for quadratic quadratic count. So this should be the count of plane rational degree D curves through 3D minus 1 points counted with this quadratic form is invariant. So it doesn't depend on the configuration of points. Right. And now the last thing I want to say in the last few minutes is, well, we know it's invariant, but it's really hard to compute. And here is a way one can actually compute this. And this is something I'm working on right now. But I think I don't have really time to explain it. So I'll just do this orally. So one very successful way to count rational curves or to count curves is to pass through tropical geometry. So instead of counting algebraic curves, you want to count tropical curves, which are just graphs. And for this, you can use combinatorics. And this can be done via a correspondence theorem, which was originally proved by Mikhalkin, who says that, well, the count of where is it? This ND, and even the one, the WD, the one with the real numbers, we can assign multiplicities to tropical curves, which are just graphs. And if I count the number of algebraic curves, this agrees with the count of graphs. And here's my theorem. Okay, my co-alpha comes first because of alphabetical order. Is that this quadratic refinement of the count of rational curves actually agrees with quadratic count of tropical curves of degree D. But I think I'm out of time, so I'll just leave it like this. Thank you very much.
Questions? Comments?
Of this one? Yeah. Okay. To you, I can explain. You probably know. So, so this tropical multiplicity of a tropical curve, let's call it A. Let's distinguish two cases. Do you know the real picture? What? Okay. Then you will recognize this. So what you do is you take the complex multiplicity. So maybe let's put a C here, which is the product of the weights of the three valent vertices of your curve. If you have only odd edges in your dual subdivision, then this number will be odd. I subtract 1, divide by 2, and I multiply this by this 1 plus minus 1. So in the real case, this will just vanish. And then I put a minus 1 to, let's say, I, and I is the number of interior points in the triangles of the dual subdivision of your curve. And this agrees with the real case. So in the real case, you just get this sign, and this is in Schuster's paper. He writes it like this. And otherwise, you should get a 0 over r. So this will be even, so I can divide by 2, and again, 1 plus minus 1. So this was the case of only odd edges, and then this is, else. So I was really happy. In the calculation, there occur other things than 1s and minus 1, but I knew from before that the result should only include 1s and minus 1, so I was really happy when now everything canceled. Yes?
You say that the quadratic type nodes, the Z, are given by the quadratic width ring. Is there an infinite number of times?
There can be, yes. Like over the rational numbers, this is an infinite number.
Pictures of split and solitary nodes.
Yeah.
What might be a picture of those types?
It's the same picture. It's like, but there's all the split nodes are the same. They identify in the Grothendieck grid ring, but the solitary nodes, there's really one type for each of these Ds. Up to squares. So you should get, in general, you should get this many types by the first relation, which I erased.
Maybe like 3 lines, 3 different lines.
No. It's locally will always, because it's a node. It will locally be of this equation, so it could only be this or a solitary node with like not complex conjugate branches, but conjugate branches, which are defined over a field extension, namely the field extension where you join the square root of.
In this theorem, so the Q side, the tropical side, you get some sort of like polynomial Q.
No, I don't get the polynomial. Maybe the Q is actually confusing because this doesn't have to do anything with the quantum things. I just put the Q there for the quadratic, but maybe I should choose a different notation. Yeah, I'm not so familiar with this quantum thing, so I ignored this. But yeah, no, I just put a Q for quadratic.
We're on the right hand side.
Yeah.
Sorry, can you, what is this number?
This number?
Yeah.
I didn't say this. This is the like count of tropical curves. Let's say they are planes. I can say of degree D and genus 0. Actually, this also works in higher genus. Through 3D minus 1 points in R2 in general position, counted with this quadratic multiplicity. So this is in GW.
So you define on the right hand side you look at tropical curves, you give them this multiplicity.
Yeah.
Right? And then so you're not saying anything about other types of multiplicities that might be associated.
No, this multiplicity. Yeah.
Is that something that? So, yeah. And then I have another question, which is so the input in order to be able to do this, you need your curve count to be given like at a 0 of some section on a like oriented manifold. That's like the input is an oriented manifold and that oriented vector bundle, and then you apply the machine.
Yeah, like this is in the real picture, but like you can replace all of this by varieties and also by oriented. You have this oriented.
But with singularities, can we have some singularities?
No, you want this to be. Yeah, I want this to be smooth. Or maybe someone has thought about this, but for now I want this to be smooth.
So smooth, like some sort of smooth space, and then vector bundle, and then you can, whatever invariant is given as the zero section, you can quadratically define.
Yeah. If you have some orientability condition, as I said, you don't need both the vector bundle and the base space to be oriented. You just need this relatively orientability condition, which is a little more relaxed.
Very good. And then, is this setting of like what cubics, but like degree 4 curves, is that fitting that setting?
Degree 4 curves? No, it doesn't really, because for the twisted cubics you had this nice smooth variety as a moduli space, and then you could just really compute this as a zero locus of a. Quadratically, we find this count of zero locus of the section of a vector bundle, and this doesn't work for higher degree curves anymore.
Whereas I guess in this case it works more.
For this one, well, this is a different setup. This is not. I mean, this is not a section of the vector bundle. I did because So one way to count this is as a degree of maps. In the beginning, I started with, I can also write, instead of the degree from n sphere to an n sphere, I can write a degree, define the degree of an n manifold to an n manifold. And one way to count this is to take this evaluation map of the points and compute this as a degree of this evaluation map at the points, where the curve should go through. And then actually the local A1 degree agrees with what it should be with this one here.
Yeah, how did you come up with this not missing?
This one here? Oh no, this was just, this was, the thing is so you have an algebraic curve, and then you just tropicalize and you get a tropical curve. So the task here is you start with a tropical curve and reconstruct all algebraic curves that tropicalize to this. And this you do like step by really patching things together from the limit. And there were different steps. In the end, I multiplied all of them, and all the terms which were not 1 and minus 1 canceled out, and this was really nice. This is a very long story where this comes from. This would take another hour to explain. So, yeah. I'll also get this question. Yes, and now I can tell you what it is, actually, with this introduction. So here, I didn't write it here, but you will only get 1 or minus 1 if you want your curves to go through to rational points. But you could also take, for example, in the real picture, you could also choose 2 complex conjugate points and ask your real curve to go through them. And you would still be able to count curves, and this would give you a different result. And now, if you do this, then you will still get only 1 and minus 1. But in this setup, if you choose your points to be Galois conjugates, then depending on where these points are defined, if you, for example, join the square root of d, you will find some bracket d in there. So.